Chapter 21, Molecular Orbital Theory. Section 21.6, VSEPR Theory. VSEPR stands for Valence Shell Electron Pair Repulsion. The VSEPR theory states that each atom in a molecule prefers to adopt a geometry that minimizes the repulsion between the electron groups in the valence shell. When there are 2, 3, 4, 5, or 6 electron groups surrounding one atom, the hybrid orbitals centered on the atom are typically sp, sp2, sp3, sp3d, or sp3d2 orbitals, such as in C2H2, C2H4, C2H6, SF4, and SF6. The elements in the third row or below can often accommodate more than 8 electrons because they can use d orbitals to hold electrons as well. Now let's look at this table. When we have 2 electron groups, the shape is linear. We often have sp hybrid orbitals. One example is C2H2. On each carbon, we have sp hybridization. When there are 3 electron groups, the shape is trigonal planar. The hybridization is often sp2. The examples: C2H4 ethylene with a double bond between the 2 carbon atoms, and also BH3. In BH3, the hybridization on boron is sp2. When there are 4 electron groups, the shape is tetrahedral. The hybridization is sp3. One example is methane. 2 other examples: ammonia, water. When there are 5 electron groups, the shape is trigonal bipyramidal. The hybridization is often sp3d. Now we'll have to use a d orbital to hold the electrons. A couple examples: sulfur tetrafluoride, and then PF5, phosphorus pentafluoride. When there are 6 electron groups, the shape is octahedral. The hybridization is sp3d2. We'll have to use 2 d orbitals. 2 examples here: sulfur hexafluoride and bromine pentafluoride. In this bromine pentafluoride, this bromine is surrounded by 6 electron groups, 1 lone pair plus 5 single bonds. Over here we have another table that summarizes the VSEPR theory. So when we have 2 electron groups, such as 2 chemical bonds, it's linear. 3 electron groups, trigonal planar. Over here we have 3 bonds. Over here, E stands for lone pair electrons, so we have 1 lone pair and 2 bonds. The molecular geometry is bent. 4 electron groups, we have a tetrahedral shape. In this example, we don't have any lone pair electrons. Over here we have 1 lone pair, therefore the 3 bonds are trigonal pyramidal. Over here we have 2 lone pairs, and then the molecular structure is bent. So we can view this as methane CH4, ammonia NH3, and water H2O. 5 electron groups. We have a electron geometry of trigonal bipyramidal electron geometry. In this case, we do not have any lone pair electrons, just 5 bonds. So the molecular geometry is also trigonal bipyramidal. But if you do have a lone pair, the molecular geometry is called seesaw. One example is SF4, sulfur tetrafluoride. On sulfur, you have a lone pair and then 4 bonds. Also, we may have T-shaped molecular geometry when we have 5 electron groups that include 2 lone pairs and 3 bonds. We can have linear as well if we have 3 lone pairs and 2 chemical bonds. When we have 6 electron groups, well, it's octahedral electron geometry. When there's no lone pair electrons, all 6 are bonds, and then the molecular geometry is also octahedral. What if there is 1 lone pair and 5 bonds? Well, in this case, the molecular geometry is called square pyramidal. So we just look at this part, ignoring this lone pair. What if we have 2 lone pairs and 4 bonds? Well, the molecular geometry is square planar. So in short, if we do not have any lone pair electrons, the electron geometry is the same as the molecular geometry. The molecular geometry is the same as the electron geometry. So when we have 2, 3, 4, 5, 6 chemical bonds, both the electron geometry and the molecular geometry are linear, trigonoplanar, tetrahedral, trigonobipyramidal, and octahedral. Now, what if we have at least 1 lone pair? Well, then the molecular geometry is different from the electron geometry. In the electron geometry, you need to consider every single electron group. In the molecular geometry, you need to ignore the lone pair electrons. So, for example, if we erase this part, the lone pair electrons, the molecular geometry would be bent, and if we erase this, the molecular geometry would be trigonopyramidal. What if we erase a lone pair electron here from the trigonobipyramidal electron geometry? Well, just pretend you don't see this E, and then the remaining structure is called seesaw. Same here, the molecular geometry is different from the electron geometry. If you just look at this top part, it's square pyramidal. And over here, one good example is water. When you look at water, there are 4 electron groups surrounding the oxygen, but there are 2 lone pairs. So the electron geometry is tetrahedral, but the molecular geometry is bent.